So I'll record these and post them either in Blackboard or on the YouTube channel. I don't know if Blackboard will allow that much memory on there. I haven't used it yet, so I'm just going to check and see. But I'll post these videos somewhere and let you know where we're going to do it, probably in Blackboard. If it's too much memory, then I'll just put a playlist in YouTube and I'll give you the link to that, which I already set up. And then I'll put the PDFs. If I actually write anything, I'll put the PDFs up. If not, I'll just post questions for each lab. This week, I didn't know that we were going to have one week 1, but when I double checked the course outline, we do start today. So luckily I checked. And what we'll just do is a bunch of linear systems. Have you had the actual lecture yet with Leon? Or no? Somebody let me know. I don't know when your class, yeah, so it was earlier this morning. 9:30 or 8 or 11. When was it? 9:30. So you've had an hour to digest. Yeah. I had one at 8 this morning and then one at 11. And now I'm doing this one. I have 3 on Thursday. One was at Concordia, and then Concordia is on strike. So I did that accidentally this morning too. So yeah, I did 8 to 9:30 this morning. And then I started my other one at Concordia in Google Meets. And then I was like, oh yeah, we're on strike. We're not supposed to be doing that. So then I stopped that one because I forgot. And then now 12:30 to 2 on Thursdays will be us for this lab. So you've seen Ian Bika at least talk about linear systems. Usually what I'll do is, because we have an hour and a half anyways, I'll do some talkie and record for the first little bit, maybe for 30 minutes, recap a couple of the topics that we're supposed to do for each lab specifically. And then I'll give you questions. And then eventually I'll start posting the PDFs ahead of time. Today, I'll just give you a few examples of questions that you can do for practice linear systems. So I'm going to guess then, based on what he had in here, I was going there in this shared folder that he gave me with all of the lecture notes. He said do 1.1 and the lab should be on 1.1 basically, which was what's a linear system and all these coefficients and blah, 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 blah. So we'll do augmented matrix. Did you see augmented matrix? Yes, somebody? Yeah. So we get a system, then we get an augmented matrix, and then we'll describe cleverly why is it matrix, what does matrix mean in Latin, and why are they using this? And then how do we use this matrix, augmented matrix, to find the solution to these systems of equations? So Lab 1, linear systems. Just to kill time, and because I like to hear myself talk anyways, I'm just going to do usually, even though they're supposed to be flipped, and I'm supposed to just give you questions and have you work on them together, and then you can ask me questions throughout if you have problems. That's what we'll do for most of the labs. I'll be here every time. I'll talk at the beginning for a little bit. So what do we want? What is a linear equation? And how do we solve them? In general, a linear equation is an equation that has every term, something separated by plus or minus or equal sign. Every one of those terms is either just a constant number or a multiple, a number times one of my variables and only one of my variables. So that says, if I'm looking at the number of variables in any equation or any term in the equation, it must be power 1 and there must be only one of the variables. So what is the general form of a system of equations going to look like? I'm going to have A11, some number times my first coefficient or my first unknown, and then plus I'm going to have some second coefficient times my second variable, and then plus I don't know how many variables I have. So I have an nth coefficient multiplied by my nth variable. And then usually we group all the numbers together and we write that as a single equation. That is the most general form of a single equation. But then we don't know how many equations we might have in a system. So Eon would show you then we'll have a 2,1x1 plus a 2,2x2 plus blah, 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 plus a 2nxn will equal b2. And then we can just keep going with that pattern. And then we will have, say, an mth equation. So we will have an a m1 times x1 plus a m2 times x2 plus all the way down to a m and xn is equal to em. And that is our linear system S. That's what we're talking about. We want solutions to that. And solutions are, they have to solve every equation simultaneously, he's going to tell you. So that's what we're going to work at this, and then what an equivalent system is, and then what this augmented matrix is, and then how we use the augmented matrix to solve these linear systems. Solving means find every single solution to these systems. And so now you can also color code if you want, and I'll add that in there. We have, first of all, we're going to have the row that we're in. This is the first one. So if you look at the first index, it doesn't change throughout the row. It'll be a 1 all the way across, or a 2 all the way across, or an M all the way across. That's the rows I'm in, or equation that you're in. And then we're also going to have the column or variable right here, 1, 1, 1, 1, 1, 1. This is column 1 or variable 1. There's an extra column in an augmented matrix because there's an equal sign here. And then we have a 2, 2, 2, 2, and then 2, 2. And this is column 2 or variable 2. And then all the way down, we're going to have an NN, an NN, and then an NN. And that's going to be column N in the coefficient matrix versus the augmented matrix. And so this is what's happening. You're going to have M rows and N columns or N variables in each of these equations. Sometimes it'll match. For the most cases, it'll be square. So then the M will equal the N, and you'll have the same number of equations as you do variables. And then we're looking for unique solutions. This is what we mean by a linear system of equations. And it is M by N is the size. And remember, M is rows, N is variables. So what is the coefficient matrix? A. This will be just the coefficient standing in front of the variables. So A is going to be A11, A12 to A1n, A21, A22, A2n, all the way down to AM1, AM2 to AMN. And the size is M by N. They will denote this. This is the coefficient matrix of this system. Eventually, we're going to use algebra and discover how to find the inverse of this. And this is one way to solve linear systems. And then we'll get the determinant of the coefficient matrix. And then if the determinant of the coefficient matrix is non-zero, then we're going to be able to use Kramer's rule to solve linear systems as well. Right now, we're going to use augmented matrices and Gaussian Jordan elimination to row echelon form. Is essentially how we're going to do it. There's going to be a bunch of terminology that they're going to fill in, or he just did, depending. What is the augmented matrix? I'm going to write it like this. This is going to be the coefficient matrix equals our column vector. So this will be equal to A11, A12, dot, 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 A1n. And then we just had a B1. The line is the equal sign, essentially. And then we have A21, A22, A2n, 2B2. Where this is AM1, AM2, AMN. Technically, this is M by n plus 1 because we have the extra column vector. This is A right here equals the B vector. And then we're going to write it as AX equals B is what it represents. But right now, this is just the coefficient matrix is the left-hand side of the augmented matrix is essentially what's happening. So those are our two matrices. Then given a system, what's the strategy? What are we going to do here? One, we're going to write the augmented matrix two. I'm going to use the 3 row operations. One, you're allowed to interchange rows. And that's what it's going to look like when I do it. Okay, 2, you're allowed to take a row and replace it with a multiple of that row. So multiplying rows by non-zero scalars. And then 3, you're allowed to take a row and add a multiple of another row to that row. Which by 2, you're allowed to multiply row J by a number. And then what this is saying is once you do that, you're allowed to add that to that row and replace it. You can add rows together to cleverly do things. What this is saying is if you have A plus B equals 4 and A minus B equals 3, do you see how to get rid of A and B and find out what A is? If you add these rows, if I'm adding row 1 and row 2, cleverly, this is the way they would ad hoc write this. In our augmented matrix, we're just going to get specific rules for this. So this is the same thing as this would say that 2A equals 7. So A is going to equal 7 over 2, which is 3.5. And then B will be 1/2. 3.5 plus 0.5 is 4. And 3.5 minus 0.5 is 3. So that's the solution. And then B will be 1/2. So this is ad hoc what we want to do in solve systems. But to help solve this linear 2x2 system, what we really want to do is use these row operations. Let me put it this way. So this is ad hoc. The systematic method would be example 1. If I have this system, A plus B equals 4 and A minus B equals 3, you could write this as, instead, if you want the two variables to be fancy, x1 plus x2 has to equal 4 and x1 minus x2 equals 3. There, now I have 2x2 linear system. Why? Because I have two equations in two unknowns, x1 and x2. Here it's a and b, but it doesn't matter. You can call them anything you want as you go through your different classes in calculus. In related rates, you would write it as Pythagoras' theorem, x squared plus y squared equals the hypotenuse squared, and then it would be some number. And so you're trying to relate two things. What do you need? You need two equations and two unknowns. These are nonlinear equations, but that's the same strategy. And so then what do we do with this? We augment the matrix, and then we use the 3 row operations. And then 3, what we want to do is, so what would I do with that? At 1, I augment the matrix. This will give me 1, 1, 4, 1, minus 1, and 3. And then what do we want to do? Once we have these 3 row operations, we want to get to REF. Which we're going to call REF. Once I have REF, hey, cats, I don't know if you can, there's some, I don't know what they're in, but it doesn't sound like they should be in whatever they're in right now. I'm going to try and ignore it. I'm probably going to, just a second. Once we get into row echelon form, what's the third thing we want to do? 3, we want to decide every time, this doesn't matter what the size of the system is, if we have no solution, 1 solution, which we'll also call unique, or infinitely many solutions. Once I do that for the system, for our example 1, what do I have? I have this augmented matrix. What are you doing? Put the cardboard box. That's one of them. This is one of the culprits. I don't know, what were you doing? Just throwing a box in there that you weren't supposed to be in? Probably. Oh, there's the other one. Go fight it. I know, go get it. They are fighting. That's funny. Attack! I have attack cats, just in case you're wondering. They attack on command. Kill! So, what am I going to do with this augmented matrix? I want to get to row echelon form. Mantra 1 of Gaussian elimination is get a 1 in the leading top corner. Check. Once I have that, eliminate below. This is why they call it elimination. We're eliminating variable x or x1 from the second equation. How do I want to do that? 1 minus 1 is 0. So I'm going to take row 2 and I'm going to replace it with row 2 minus row 1. And that will give me a 0 in that spot. And that's what I want. And then for 2x2 matrices, that's essentially row echelon form. What's the matrix I get once I do that? I did not change row 1, so I will do this. Just copy it out. Now what I'm doing is I'm replacing every entry with the entry of row 2 entry minus row 1 entry. So 1 minus 1 is 0. That's why I did it. -1 minus 1 is -2. And 3 minus 4 is -1. Now, what I really want to do is Math102 is once that's done, essentially what we have is we have a leading 1 and we can ignore the top and left corner. And I want to focus on the next spot. I want to get a leading 1 there. In this case, because there's only 2 equations or I'm lazy, I'm just going to divide by -1/2 and then I will get a 1 in that spot. This says I'm going to do row 2 goes to the type 2 of my row operations, the row operations. These are the 3 row operations. And I'm going to multiply by -1/2. What does that give me? That gives me a nice, this is a row echelon form, but this gives me a nice row echelon form, which says 1, 1, 4, 0, 1, 1/2. This is REF. In REF, you should know that you have a unique solution when the number of leading entries, in this case both 1s, equals the number of unknowns you had. Then that implies what? We have a unique solution over the original unknowns we had. What does that tell us? We have a unique solution. What is it? Well, from the augmented matrix, we have, it didn't change. We still have x1 plus x2 equals 4. And now we just have, we can just read off x2 equals 1/2. That's the system, the new system we got from REF. Turning it back into that system, now we use back substitution. This says x2 is 1/2, so we've got that. And this says x1 is equal to 4 minus x2, which is 4 minus 1/2, or x1 is equal to 7/2, just like I did ad hoc. This says the unique solution of what? X1 equals 7/2 and x2 equals 1/2. That's the unique solution. Yes. Also, we can draw this pictorially. What was this saying? If you want to draw this, if you draw this as x plus y equals 4 and x minus y equals 3, let's turn that into calculus because we have power at calculus. And what can we do with that? Now let's number off our axes 1, 2, 3, 4. Try to make them the same. 1, 2, 3, 4. 1, 2, 1, 2. So now there's a labeled axis. What are our equations? Usually I write this as from equation 1, I would get y is, if I wanted in mx plus b, negative x plus 4. And then from equation 2, I'm going to get y is equal to x minus 3. These are the two straight lines I have. we just write it as a system. But yes, as the system S, you can view this as two lines, and we're saying find all the points in the plane that are on both of these lines, and there's only one point, their point of intersection. So now let's draw both of those lines, and sacre bleu, it will be right here where we should expect it when x is 7/2 and when y is 1/2 is where we should expect them to intersect, right there. When I draw these, how do I draw them? So for the first one, it should be every straight line is uniquely defined by 2 points. So I look at when x is 0, implies y is 4. And when y is 0, the x and y intercepts. When y is 0, x is 4. And so that's the straight line. Y equals, or x plus y now in your linear algebra land. That's the representation of x plus y equals 4. Now what we do in linear algebra is we put all the variables on the same side. And we actually solve for the y becomes the dependent variable and x becomes the independent variable. Don't worry about it right now. Solve the linear system using the Gaussian elimination. Now what's the pink one? For the pink one, the same thing. I just need 2 points. So when x is 0 for the pink one, y is -3. Oh. And right. And then when y is 0, this says x is 3. So that will give me the point 0, -3. And x equals 0, y equals 3. And look at where they intersect, right at our point, unique point, 7/2, 1/2 is their intersection point. When the lines are parallel, there can be no solution. That's what we're going to get in 2 dimensions. Lines that are parallel or multiples of each other can never intersect. And when we get that it's the same equation in this, and we only give them one, we'll have infinitely many solutions. That's 3 cases. In the other case, what do the other cases look like? If you look at my videos on YouTube, you can go to the YouTube videos. I'll put all of these videos probably in there because I have a bunch of linear algebra ones on a lot of these topics, or I'll make other ones. Engineering topics like start to differ halfway through than the regular linear algebra. But what does the other ones look like? If I do example 2, what if we do x1 plus x2 equals 4 and x1 plus x2 equals 3? These lines are parallel. If we look at this, you can rewrite this as and then what we're asking when we say solve this, we're asking find all points in the plane that are on both of these lines, but these lines are parallel because they have the same slope. So if you write this as, again, in calculus form, we would have y equals -x plus 4, the same one as we did in the last time. But now in this new equation, we also have y equals -x plus 3. And so we have m2 is equal to -1 and m1 is equal to -1. And what does the mean value theorem say from calculus? The mean value theorem says that the instantaneous rate of change has to equal the average rate of change. These are slopes. When are slopes equal? When they're parallel. The lines are parallel in the mean value theorem. Here, what does this say? That if this is L1, and this is L2, then L1 is parallel to L2 if and only if M1 is equal to -1 equals M2. So they're parallel. Therefore, there can be no point in the plane that's on both of these lines because they never intersect. This is the definition of parallel. I can deduce this from calculus, but what does it look like in linear algebra land? In linear algebra land, what am I supposed to do? 1, augment the matrix. So I get 1, 1, 4, 1, 1, 3. My mantra is get a leading 1 in the top corner, kill below, eliminate everything below that leading 1. In this case, I already have a leading 1. So what I'm going to do is I'm going to do row 2 goes to the same move, row 2 minus row 1, but this time I'll get a contradiction. Be careful. This is what trips everybody up. What will that give me? This will give me 1, 1, 4 to get to RAF until, for now, equation 1 will never change. She's playing with the chords in the bottom. Sorry, I had to lure her out. Here's another one. Alice. Sister, yeah, get over there and do something. Don't do that. Row 1 will never change. And then now what am I doing? 1 minus 1 is 0. 1 minus 1 is 0. And then 3 minus this is -1. So what does this say? If I turn this back into the system, this says x1 plus x2, this is REF, equals 4. And then now this says 0 plus 0 equals -1. That's a contradiction because you can't have 0 does not equal -1. So this 0 equals -1 if and only if there's solutions. Let me write this like this. In this case, 0 equals -1 if and only if solutions to system. That's the thought here. And then i.e. there's no solutions. Because 0 doesn't equal -1, I hope. And so this is what it looks like. In the last row, this is what it's going to look like. In the first one, the last row looked like this. The last row is what tells me always, the last non-zero row. It tells me whether I have infinitely many solutions, one solution, or no solution. If you get in the augmented matrix, no matter how big this thing is, if in the last row you look and you have the same number of leading ones, we have 2 leading ones or leading entries, and we had 2 variables originally. That's the calculation in my brain every time that says I have a unique solution, and then I can back substitute or go to reduced row echelon form to find out explicitly that the solution is 7/2, 1/2. There will only be one. Now there's going to be no solution. What does that look like? That looks like, Kenny. That looks like in the last row in row echelon form, this row tells me I get zeros on the left-hand side, non-zero on the right-hand side. This is perfectly okay. If I had 1, 1, 4, 0, 1, 0, that's an REF also. This is okay. This says x2 equals 0 and x1 equals 4. That's a unique solution. Why? Because the number of leading entries equals the number of variables I had originally. So 1 equals 0 is okay. 0 equals -1 is not okay. People get tripped up by this scenario. This is not the case of no solution. This is a unique solution scenario. One of them is 1 equals 0, but this says 1 times x2 equals 0, and that's perfectly valid. That's perfectly valid. And then finally, and then I'll be quiet and just give you some systems to solve, or a couple systems at least. What does example 3 look like? Oh, pictorially, what's happening here? So we already saw at 4 and 4, not to scale, I guess. This was the first one. This was y equals negative x plus 4. And then if you do the other one for the other one, you can do it quickly. Y equals negative x plus 3, but you're going to get 3 and 3. And so then if I can draw it nicely, they're parallel. There's no solutions. And that's why in especially 2 dimensions, but this is in all dimensions for m equations in n unknowns, there's only one solution, no solution, infinitely many solutions based on planes and hyperplanes and everything else in higher dimensions. But the same analog is essentially true. If they're parallel lines, there are no points in the plane that will be on both of them. So there can't be a solution algebraically. And then example 3, what's the third case? When I give you x1 plus x2 equals 4 and 2x1 plus 2x2 equals 8. That's the same line. And what it's doing is just multiplying equation 1 by 2 is equation 2. And so that didn't give me any new information. How many points on the plane are on the same line? All the points on that line. So there will be infinitely many solutions on that, and we get a parameter t. And then in higher dimensions, this becomes more useful, and we'll get more parameters. The number of parameters is the dimension of the space that you're finding, which is the solution space of all of the solutions to these linear systems of equations. We'll let Eon get there. For now, one solution, no solution, infinitely many solutions. What are you ruining in there? You'll be throwing things out there. We show you how to solve these systems. The cats are throwing stuff right now. I think she just dumped a giant container of cat treats onto the ground and probably broke the plastic, I think is what I'm hearing right now. Augment the matrix. It doesn't matter where it came from or whether the solution is. How do I tell what the solution is? In the last row, non-zero row, or last row, if it is 0 in this case, of the REF is where I'm going to decide whether I have one solution, no solution, or in this case, infinitely many solutions. So I write this down as 1, 1, 4, 2, 2, 8. This is the augmented matrix. I have a leading 1, so I want to kill below. This time what I'm going to do is I'm going to do row 2 goes to what? Row 2 is going to get replaced with row 2 minus 2 row 1, because I'm going to multiply every entry in here by -2 and then add it to that entry and then get a new entry. When I do that, to get to REF, which this will be, I don't have to change row 1. That'll be reduced row echelon form eventually. But row 1 shouldn't change when you do this. The other rows should. Now what do I do? 2 minus 2 is 0. 2 minus 2 is 0. 2 minus 2 is 0. So what that says is 0 equals 0, and that's always, i.e., we can let y equal t be free. So y became the independent variable, or sorry, why is it y usually when they phrase it like that? Because I want to write x2, the highest index variable. Doesn't matter, that's our convention, to be free. What we mean by that we're letting t be any free number. There's no restriction. When is this true? What's 0 times t? 0. So that's always true. So is there a restriction on t? No, there isn't a restriction on t. And then what is x1? Well, x1 is equal to 4 minus x2, and that's 4 minus t. And so what does that give us? Infinitely many solutions. thus infinitely many, that's my lazy way of saying infinitely many solutions. One for all and all for one for each variable parameter t. What is that infinite solution set? We said that x1 is equal to 4 minus t and x2 is equal to t for any real number. That's the solution set. So maternal. Mat means mother in Latin. Rix is womb, essentially. Womb of the mother. So matrix means womb, essentially. Why are they calling it like this? If you can find out and understand why they called it the weird thing they called it, the math usually makes more sense. It has all the vital information and gives birth or rise to the solution every time. Vital information. And I can clean that up. Gives birth to the solution every time. And in REF, we can always tell and then one do that. Always, I said. If there's one solution, no solution, or infinitely many solutions. The number of rows of zeros, in this case, the last thing is the last row told me that the row of zeros told me infinitely many. So if there's no contradictions above this, the way that I tell is I take a matrix, I augment it, I get to row echelon form using these 3 row ops. If I get to REF and the number of leading entries is equal to the number of free variable or unknowns I had originally, then there must be a unique solution. And I use back substitution to find it. And that's the intersection point of the lines in the 2-dimensional case. If I have a system and I augment the matrix and I get a contradiction like this one. And so in this augmented matrix, if I get a 0 equals non-zero somehow, this will tell me that in the last row, I can say that there is no solution. And then if I have 0 rows and there's no contradictions above them, that last row being 0 tells me I have infinitely many solutions. And then I let however many variables there are. Notice that which one did I pick to be the free variable? This one has a leading 1, but x2 has no leading 1. And that's what I made the free variable. So you can tell in here, this column, this had no leading, there was no leading variable in that second row. So x2 didn't have a leading 1 spot like this one did. Here it did. So they're both not free to be anything. They have to be a unique one thing. If instead you get that somebody's missing in one of the columns, so there is no leading entry for that guy, he's not a unique value, he's free to be anybody, and that's how I pick him to be free classically. X1 had a leading one, so he's not free, he'll be fixed down and he'll depend on X2 or T. X2 is the one I set to be free. I can tell in the column when I get that. Any other questions? So normally I'll have this prepared this weekend, and then for our labs every Thursday, I'll have a PDF usually up with a few questions that you can do to try this similar type of stuff. But this is how the labs will go until they let us go back to school, at least. I still don't want to meet you guys. You need to see me in person. Then we have to go to McEwen. I guess I'll be there in the morning anyways. I teach at Concordia from 11:10 to 12:25, and then I'm supposed to teach you guys on Thursday at 12:30. I'm like, how am I supposed to run in 5 minutes? But I'll figure something out. It's like it was supposed to be online, and then they keep changing everything. So eventually this is what will happen. For the first few minutes, I will talk about the topics that we're supposed to talk about, etc. And then we can use the rest of the class just as I can turn my camera off. And then if you have questions, etc., or practice problems that I put up the PDF, I'll put the PDFs on Blackboard, and then that'll be the questions that you can try on there. Then there'll be quizzes based on the quiz days. I'll let you know when the first quiz is, usually the week before, but the first quiz is until like week 4 or something like that. Where is it? Just a second. Where is this? The lab schedule is the last page of your course outline, by the way. And then it says test 1 is lab 5. So we have in the 5th week. So in the 4th week, I'll remind you we have a quiz based on the first few labs. Any other questions? Otherwise, let's do some problems. You can start with this one. And then in each week, as we start going, I can discuss the solutions / post the solutions of the previous problems. In the next week, we'll sort of stagger it and talk about those ones and then talk about some new problems. Eventually, you can bring me Eon's horrible assignment questions or whatever too, and we can discuss some of that possibly in the hour and a half. So the first one, let's do email. So you can start with that one. I'll turn my camera and my microphone off. If you have any questions, just let me know in the chat, etc. But for now, we'll use the rest of the time, or you can have your weekend back, and I'll see you next Thursday. But try this one. I'll write a couple more down. But cat's being a pain in the butt anyways. So unless you got questions, etc., have a good weekend, and I'll see you next Thursday.